we'll get started for today. So let me just recall what we did last time because we were kind of rushed at the end. So last time, well, we finished the proof of the C-law theorems. And we did the simplicity of the alternating group. And then actually before we did any of that, we did example of so we did the example of groups of order 15. Okay, and so I think after we did that example, we talked about, so you guys worked that out at the start of the class, and then we talked about it a little bit. And I think I suggested that at some point that maybe you could think about that for like how to generalize that. But so we'll talk about that more today. So today we'll talk about generalizing this to groups of order PQ. Yeah, so if you don't remember the example, the answer to like what are the groups of order 15 was Z mod 15Z is the only group of order 15. And so we can and so when we did that proof, well, we talked about a few different ways to do it, but one of the ways we did it sort of bridges into this idea that we'll talk about today of semi-direct products. So just to say out loud, when we were doing these groups of order 15, like we said, okay, there's a CELO 5 subgroup, and then there's a CELO 3 subgroup, and so there was a unique one of each. And well, since they were both normal, you could actually sort of just use the homework problem to finish arguing then. But if you didn't want to do that, we sort of went over this sort of more systematic way you could think about it, where you took the CELO 5 subgroup, and then which was normal, and then you sort of took this other subgroup of order 3, and then you just looked at the fact that like this other subgroup of order 3 acted on that sort of CELO 5 subgroup by conjugation. So we knew what the automorphism is that. So that gives you a map from Z mod 3Z to the automorphism group of Z mod 5Z. The automorphism group was Z mod 4Z, and so sort of that map had to be trivial, and that means sort of conjugation sort of fixes everything. So sort of that gave you that the two groups commuted. And so semi-direct products are sort of about generalizing, systematizing and sort of generalizing this kind of argument. Okay. So maybe, yeah, I should just say a little bit about where we are and how that fits in with things. I mean, well, we're still talking about finite group theory, and I think we're still sort of in this process of using, studying just the structure of finite groups, using this idea that sort of you can take the notion of a group action and then sort of just you can take the internal structure of finite groups and like the existence of subgroups, the conjugation action, you can use that to sort of produce many different group actions, which then you can in turn sort of use the theory of group actions to sort of understand and sort of give you results about your group. And so that's sort of, those ideas like really culminated with proving the C-law theorems. And so the C-law theorems is like this very strong thing that gives you control over like the existence of normal subgroups, and sort of tool. I really made the thing away. It gives you ways it gives you sort of a set of ways you can sort of try and prove things are simple and also or not simple and sort of find normal subgroups. Like it sort of gives you a way to sort of produce structure just from knowing the order of a group. So that was sort of the culmination of that theme of sort of using the group actions on sort of the internal structures of the group in order to sort of deduce concrete statements about what sort of groups of certain order can look like. I mean, the overarching theme of finite group theory is you want to sort of understand something about the classification of finite groups. And right, and so the Jordan-Holder program, which I outlined at some point, says you sort of want to split this up into two parts. You want to split it up into like finding all of the simple groups. And so and Seelof theorems are good for that because you can sort of rule out like the existence of simple groups of certain orders, for example. So you want to sort of find simple groups, and well, we at least gave one infinite family of simple groups by looking at the alternating groups for n greater than equal to 5. And there's also sort of the basic example like Z mod PZ, so we know what sort of the simple abelian groups are. So now we have sort of some simple groups to work with that we can sort of try and build other things out of. And that's sort of the second step of the Jordan-Holder program is sort of once you understand what the simple groups are, you also want to understand how to build other groups out of simple groups. And that's not something you can always handle with semi-direct products, but that's sort of how you can think about it. And this is a tool sort of for building new groups out of old groups. Well, I don't know what I mean by new and old groups, but say, so combining two groups to build a new group, let's say. Okay, so yeah, and it's a useful tool for that. And it's useful not just in this, in some ways, ridiculous abstract project of classifying finite groups. It's also useful for like actual applications of group theory to like, yeah. So and the past few weeks have been like lost in the weeds of just like what is the structure of finite groups, but I mean, let me recall that at least at some point I made the point that the reason we care about groups is not because they are things that exist. Like we care about groups because they act on other things that are interesting. And like the second half of the class will be all about exploring sort of how exploring interesting group actions and sort of using group theory to understand them better. So in particular, the study of Galois theory, which will start after the midterm, is about sort of using group theory to understand sort of the field extensions and roots of polynomials. So sort of this more somehow tangible, interesting problem, at least for a number theorist. And semi-direct products will also be, semi-direct products are a tool that will also be useful for understanding things that actually show up in applications. So it's not sort of, you shouldn't think of semi-direct products as just some sort of some abstract construction that shows up in the classification of groups. Like semi-direct products are sort of a useful way of understanding structure that actually arises sort of in nature. So it's not just abstraction. Okay, so let's do an example to start things off. So let's look at my favorite group, at least in terms of, if you measured favorites by the number of examples I've done, D8 is probably my favorite group. So this is the symmetries of the square. Okay, and so inside of D8, we have a copy of Z mod 4Z, which is normal. So this is just rotations. So, so one inside of here. So if I have sort of K and Z mod 4Z corresponds to rotation by 2 pi over K. Sorry, that's not a good way to say it. Let me try that again. Z mod 4Z, this corresponds to rotation by K times pi over 2. Yeah. for various reasons, I'm used to writing Z mod 4Z as 1 over 4 Z mod Z, in which case what I wrote before was correct, but this is obviously not what I wrote right now. Great, so this is rotations. And so this is a normal subgroup. You can check this easily just by sort of direct computation, or you can invoke this fact we saw, I think, on the homework. Yeah, I think this was on the homework that if you have a subgroup of index 2, it's always normal. So a subgroup of index 2 in any group is always normal. Okay, so this is a normal subgroup. We have sort of also some sort of complementary subgroups. So we also have this line L. And let me just write sort of R sub L for reflection along this line. I mean, we also could reflect along a diagonal or along the other vertical, the horizontal line. So those are 4 other reflections. Let me just use this one, but what I'm about to say, you could use any of those. And this is sort of an important point. So you have reflection along this line, L. And so the subgroup generated by RL is just a copy of Z mod 2Z. So now it's just a subgroup of D8, no longer normal. It's easy to check this sort of if you conjugate. In fact, this is a computation we've already done, but if you conjugate sort of this thing by a rotation, so you end up moving it to a different reflection. And I think there are two different conjugate classes. This sort of this reflection conjugates to the reflection. The reflection I've drawn sort of conjugates to the horizontal reflection, and then the 2 diagonal reflections are conjugate to each other. Okay, and so we have the Z mod 2Z in here, and so we have. Yes, let me sort of. Okay, and so we have. Let me give it this rotation by 90 degrees name. Just otherwise, I think my notation is going to get a little confusing. So then we have this subgroup generated by S, so the subgroup of rotations. And we have this subgroup generated by this reflection. And this is all of D8. And sort of moreover, so why is this all of D8? Well, it's just because we know if I have a subgroup H and K, and the size of H times K, so this is sort of the set of all elements in the product. So we've seen this a few, maybe last week, I guess, maybe last Tuesday, that the size of HK is just the size of H times the size of K divided by the size of H intersect K. So in this when K is normal, or when H is normal, which is this case, this is not just a numeric identity, but we have the index of H in HK is equal to the index of H intersect K in K. And now these are really, when H is normal, this is a subgroup, and so it sort of makes sense to sort of use this. In fact, we have more. We have HK mod H is isomorphic to K mod H intersect K. So this sort of identity thing. You can sort of, if you multiply out these, if you rearrange these terms right here, you can re-express it as sort of this identity of indices right here. And this expression, this identity of indices is just sort of the manifestation on sort of cardinalities of this isomorphism of groups. Okay. Sorry, that was a little bit of a side note, but here the point is, I just wanted to say that sort of the product of these two subgroups gave me all of D8. And the reason is because, well, this is a subgroup of order 4, this is a subgroup of order 2. Their product contains 8 elements because these subgroups don't intersect at all. So these subgroups don't intersect at all, so their product contains 8 elements, so it really has to be all of D8. But they don't intersect except for the identity element. Are there any questions about that sentence? Sorry, that was maybe a little bit garbled. Okay, good. So what this tells us is somehow we can get every element in some of the group sort of by multiplying sort of elements in Z mod 4Z and Z mod 2Z, sort of viewed as these subgroups. So let me sort of say that in a different way. So we know there's a identity of sets, bijection, say. Which sends Z mod 4Z times Z mod 2Z, so just to D8. This just sends K J to R to the K times S to the J. So I mean, this is a bijection of sets. It's not a group isomorphism. Because, I mean, well, the direct product on the left-hand side, like that's an abelian group, and this D8, this is a non-abelian group. So this is definitely not a group isomorphism, but it is a bijection of sets. And so, I mean, you can sort of change the idea of a semi-direct product is you want to change. So in this setting, you want to change the group law on the set Z mod 4Z times Z mod 2Z. So that this becomes a group isomorphism. So this is sort of capturing this idea we had like in this previous example of groups of order 15. Because where is this actually, like where is this new group law going to come from? Well, we're just going to sort of express the group law over here and then translate it back. So let's see what happened. And conjugation is going to show up. So let me see what this means. So this new group law should have sort of K comma J. Let me sort of write this new group law as a star to indicate that it's not sort of the standard group law on this set. So K comma J are K prime J prime. Well, and this should match up with R to the K S to the J times R to the K prime S to the J prime. mean, I want to just, and literally I'm just sort of taking the group law over D8, and I'm transporting it to a group law in this set via this bijection of sets. So sort of by definition, this is what I want the group law to satisfy. But now I can evaluate, and I can just evaluate this to figure out what I need to do. So this is going to be equal to, I can rewrite this. So let me pull it down. This is r to the k, to the j, r to the k prime, to the j prime. And I want to bring the s's and r's together. So to do that, I have to sort of commute these two past each other. But then we have the standard trick we use for that. So we have r to the k, s to the j, and then we multiply this by right, I both should. So which ones do I? Yeah, sorry, I always get this backwards. So 1 second. So I should multiply by this by sort of s to the minus j prime. Sorry, s to the j prime. Right, so I want to, yeah, sorry. Let me try to write this again. So I just want to yes, sorry, I'm slow at this kind of computation. So I want to rewrite this s to j r to k prime. I want to sort of swap the order of multiplication. So to do that, I write this as r to the k prime times but maybe the issue is I've done this backwards. Sorry, now, yeah. So I have a times b, and I want to write this as this one is in the normal, not normal subgroup. This one's in the normal subgroup. Great, okay, so this, so I should write this as a, b, a inverse times a. So I got distracted by my indices. So and that's the situation we're at in here, right? I want to get all the r's together and I want to get all of the s's together. And so I have to sort of move, like I have to move this s past this r. So I have to sort of understand how to commute that past. And I can do that by sort of just rewriting a times b as a, b, a inverse times a. Because sort of b is contained in normal subgroup. So this is still sort of in the same normal subgroup. Okay, so let me sort of just tell you how this computation works out. So if I do, in this case, so if a is equal to s to the j, so this rotation by sort of 2 pi over j, or sorry, by j times pi over 2, and then so this is rotation by j times pi over 2, and b is equal to r to the k. So it's either sort of just identity or it's flipping by this, it's this reflection. Yeah, so R is for reflection, not rotation, sorry. Okay, so if I do this thing, I get sort of A, B, so I get S to the J, R to the K is equal to S to the J but sorry, I did the wrong one again. So now I've gotten lost in my own notation. Okay, start over. Let me start over. So this might have been a bad day to solicit input about my class. Okay. Try this again. So here's yes, sorry. We want to have so I just wrote everything wrong is the problem. So this is so I got everything sort of backwards in terms of my what I'd called what. So let me try this again. So the point is sort of this Z mod 4Z on the left was supposed to be this group of rotations. So sort of this K was supposed to be S to the K. And this J was supposed to be R to the J. So the J is in Z mod 2Z. And so the point was it's supposed to be S to the K prime, R to the J prime. Okay, and now this looks much better, so I can continue. So because I can rewrite R to the J S to the K prime. So this is what I was sort of trying to do before, as R to the J S to the K prime, R to the minus J, times S to the times R to the J. And if you think about how rotation sort of interacts with reflection, so you can work out sort of this following step is just an exercise in the definitions. This is equal to this is equal to S to the minus J times K prime. Sorry, minus 1 to the J times K prime. So if you sort of if you conjugate rotation by reflection, sort of it just becomes sort of the opposite rotation in this case. Okay, so times R to the J. And so this sort of gives me my new law. So Kj star K prime J prime is equal to oops, I didn't finish my computation. So now I need to substitute this in. So we get S to the K times S to the minus 1 to the J K prime times R to the J times R to the J prime. So that means that we should define our group law by saying Kj times Kj prime is equal to K plus minus 1 to the J times K prime J plus J prime. So on this sort of Z mod 2Z factor, we didn't change anything. But now sort of we change, like what happens in the Z mod 4Z factor sort of depends on actually what was in the Z mod 2Z factor for the first entry. And that's reflecting the fact that like in this D8, like we can't just move, like we can't just commute multiplication by R and multiplication by S. Like we can't commute multiplication of a rotation and a reflection past each other. When we try to do it, so we introduce this conjugation action right here. So we introduce conjugation, and that conjugation like changes what you get. So that's sort of why sort of this first factor gets changed, and sort of the thing gets changed by only sort of depends on the second factor in the first element in the multiplication. It's because this is the thing that you're sort of trying, like, we had to move the R to the J past the S to the K prime. And so that's sort of where we introduce some sort of twist in our multiplication. Right? And this is sort of like a twisted multiplication. Okay, and so what's the conclusion? Sorry, let me zoom in and scroll up. So the conclusion is we have this group D8, and inside of here, like, we have rotations, and we sort of just fixed one other reflection, and we sort of knew that we could get anything sort of uniquely as a product of some rotation and sort of either that and some power of that reflection, so that reflection or an identity. So we sort of had these two subgroups such that sort of together you can write any other element sort of uniquely as a product of the things in those two subgroups. Okay, and then so that means there's a bijection sort of between the product of the two subgroups and the whole group, which is just a bijection of sets. But in order to like use that bijection to sort of then describe the group operation over here, like you have to introduce some twist. So here's this twist. Instead of just adding k plus k prime, we look at k plus -1 to the j times k prime in this case. And the reason we had to introduce that twist was because when we sort of tried to commute R and S, so when we try to commute the two elements of this thing, like, well, the group's not necessarily abelian, so we sort of introduce some conjugation. So if the group was abelian, this conjugation would just sort of wouldn't change anything. I just get S to the K prime. But here, because the group's not abelian, like we really, in this case, actually get something. Okay, so that's the general setup. Let me put that general setup into words. And so what we've just said, let me put into words. Yeah, let me give a name for what this thing, let me give a one-sentence summary of what we just said in this example. So the example says that D8 is isomorphic to a semi-direct product of Z mod 4Z with Z mod 2Z. So now I'll define what this means, but sort of there should be sort of a subscript here. So my subscript I'll write as phi, where phi is a map from Z mod 2Z to aught to the group automorphism of Z mod 4Z. Well, and it's just sort of it's the map you get by the conjugation action of Z mod 2 on Z mod 4 here. And so this was just given by 1 goes to multiplication by -1. So the generator in Z mod 2Z goes to multiplication by -1, which is an automorphism of Z mod 4Z. That describes this map. So this notation Z mod 4Z, then semi-direct product Z mod 2Z with the subscript phi, what it means is exactly sort of we take just the set Z mod 4Z times Z mod 2Z, but then we equip it with a twisted action coming from this map. So let me sort of state that more carefully. So definition / theorem. Okay, so if H and K are groups, and phi so phi is a map from K to the automorphisms of H as a group, then the set. So H semi-direct product phi of K is the set H times K equipped with the multiplication H1 K1 times H2 K2 is equal to, in practice, you would just sort of write this out. It's normal, but let me emphasize, let me just give it a name here. So this multiplication really the underlying set doesn't care about this map phi, but the multiplication law on this underlying set cares about the map phi. And this is equal to H1 times phi of K1 is H2, then K1 times K2. So on the right-hand side, just like in our example, the multiplication doesn't change, it's K1 times K2. But on the left-hand side, you take H1, but you don't multiply H1 by H2. You multiply H1 by the automorphism phi of K1 applied to H2. So in this whole thing I'm highlighting right now is an element of H, because phi of K1 is an automorphism of H, and I'm just applying that automorphism to an element of H, it's H2. So here, in our example, this was this -1 to the j times K prime. Was sort of, so this -1 to j was sort of phi applied to j. And so there's an automorphism of Z mod 4Z. And so then, well, this is the definition. The theorem part is that this is a group. So this defines a group. So, and there's some small thing to check, and this is just a simple exercise, so I'm not going to work it out, but you have to check that sort of this still satisfies the associative law. There's still an inverses, there are inverses, etc. This finds a group, and so the map H goes to the semi-direct product. It sends sort of just an element to just little h comma 0. Well, this identifies H with a normal subgroup of the semi-direct product. Then K, so we do the same thing, but we map the K to the second component. This identifies K with just a subgroup. And sort of under these identifications, I think of K as being a subgroup, and then I can look, so that means I can conjugate an element of H by an element of K in this group law. So here the multiplication is sort of by this group law above. And let me be careful. So this really means when I wrote KH, K inverse here, I mean, under this identifications, that means H0, 0 K star phi H0 multiplied by 0 K inverse. happening there? Well, this is just equal to phi of k. Of h. I.e. So, how can you think of this? This is essentially reversing the process we did above. So in the process, we did we're doing this example for D8. We sort of started with this group, and then we looked at we had this normal subgroup of rotations, and we had this this complementary subgroup of reflections. And then we said, okay, so I can write everything as a product of sort of an element of those two groups. So I sort of had this set bijection, and then I just said, okay, let me sort of write down the sort of induced group law I get on that set from sort of having this bijection. And like if you think about what was happening there, like really this sort of twist in the group law was coming from the conjugation action. So of the subgroup of reflections on the subgroup of rotations. Maybe we write that here. Conjugation of a rotation by reflection. And so then what this sort of definition / theorem is saying is that actually you can sort of start the other way. You can just start with two abstract groups. So you have two groups H and K. You can sort of give a map from K to the automorphisms of H. And then you can construct a group such that K is a subgroup and H is a normal subgroup. And the conjugation action of K on H is sort of given by this specific by this specific map. And so yeah, so checking this works sort of is trivial. So yeah, so we already saw not trivial, but it's just a computation. So you sort of should do however much of that computation you need to do to sort of believe this on your own. Right, and so the dihedral group D8 is an example of this. And more generally, let's see more examples. The dihedral group on 2n, or sorry, so not dihedral group on 2n, so the dihedral group of order 2n. So this is symmetries of the n-gon, of the regular n-gon. And this is isomorphic in the same way to Z mod NZ, semi-direct Z mod 2Z, where you can take a reflection. Right, and so yeah, and let me not sort of specify exactly what element you get in here. You can think about that as an exercise. Should probably depend on the reflection. Well, I'm not. Well, now I'm not sure, but So anyway, this, well, okay, good. So exercise for me too. So exercise to figure out, so what the actual, like, exercise for home is, what is phi? In this presentation. And you can get this the same way, I mean, as in the example of D8. Good. So let's see. Let me say, oh yes, let me say one more example, then we'll take a break. Sorry, I guess it's been a little long to not have a break. When for any group H, you can just form the group, I take the semi-direct product of H with ought H, where sort of phi is the identity map. So I can sort of, I mean, this is sort of maybe conceptually helpful. So we didn't, and there's a whole section in Dumb & Foote that we basically skipped about automorphisms of groups. Like one of the things, so if you think about when you think about automorphisms of groups is like, well, there's a standard source of them, which is conjugation. So like, if I have a group, I can get an automorphism of that group by conjugating by an element of that group. It's like any group H, like conjugation by an element of H, that's an automorphism. Moreover, if like if I can embed H in another group as a normal subgroup, that I can also like conjugating by any element of that other group also induces an automorphism of H. And it's sort of a natural question to ask, like, is every automorphism of H sort of realized as conjugation by some element when you sort of by H living as a normal subgroup in some other group? And like, so this says the answer is like tautologically yes. So this sort of gives an example where all of the automorphisms of H are realized by conjugation by some element of this sort of bigger group where H is a normal subgroup. So it's not a very interesting answer to that question, but it is a like a nice tautological answer to that question. Right. So right. Well, so let's go ahead and take a break, a longer break. So we'll take a break till 1:30, I guess, and then in the last 15 minutes, we'll come back and we'll just we'll go back and look at sort of what about the dihedral group and sort of these subgroups of the dihedral group let us sort of get this identification with a semi-direct product. So we'll just sort of state that a little bit more clearly. But this is sort of one of the things that's useful about dihedral group is, or about semi-direct products, is sort of, it gives you a way to sort of take an abstract group and sort of sometimes break it down into sort of two smaller pieces in sort of a formal way where you understand a little bit better what's going on. Like, somehow we understand these two cyclic groups very well, and then this is saying we can this is telling you how to understand the dihedral group completely in terms of these two cyclic groups, and then there's sort of this little twist in the multiplication. So it's sort of a useful way to like break things down into smaller pieces, even when that's more general than a direct product. I mean, you can find a lot more semi-direct products of groups than direct products of groups. And okay, yeah, so and hopefully we'll do groups of order PQ, but we'll see. So let's come back at 1:30 though. Okay, so we'll come back. So let me just state sort of the recognition principle here for semi-direct products. So we started by looking at this dihedral group, and so we had like these actually specific subgroups of the dihedral group, and we were able to identify sort of the dihedral group with sort of some twisted product, a semi-direct product of those two subgroups. Then we sort of talked about that construction in general, where you sort of take two just abstract groups with sort of this map phi from one to the automorphism group to the other, and you produce a semi-direct product. So that's this twisted group law and sort of just the product of the two sets. sorry. Excuse me. So you get this twisted group law in the product of two sets. And now we just want to sort of go back and connect the two. We want to sort of state when, like, if I have a group and I have sort of two subgroups that satisfy some certain property, like, then say generate the group. Like, I want to sort of know that that group is actually isomorphic to the semi-direct product. So that's what sort of I mean by a recognition principle. So there's this, I don't know if you want to make it or not, but at least classically you make this distinction between internal semi-direct products, where you're sort of living inside some subgroup and you just like look at the group, the subgroup generated by these two things, and external semi-direct products, which is this abstract construction that that we just carried out. And well, okay, let me just say the recognition principle, and sort of it will make it clear what one needs to know anyway. So if G is a group, H is a normal subgroup of G. Let me even say it a little bit. Let me say it slightly differently. H is a subgroup of G, and then K is a subgroup of the normalizer. So K is a subgroup of the normalizer in G of H. Then well, now we know sort of the set of products, H times K. This is a subgroup. So this is something we've seen several times before. But if you take a subgroup and then sort of a subgroup of the normalizer and you sort of write the products. And let me say further, so and if H intersect K is just the identity element, then the map H comma K goes to H times K is an isomorphism. It's a group isomorphism. From the semi-direct product of H and K to HK to HK. So here, the semi-direct product is given for the map phi, where phi is just given it's the natural map from K. K is a subgroup of the normalizer in G of H. This sort of goes by conjugation. So everything in the normalizer goes by the conjugation action to the automorphisms of H. So that's the point. If you like if you start with these two subgroups that sort of satisfy this property, then in fact sort of the group they generate just by taking their like the group you get by taking their products is sort of, so that's a subgroup of G. So this is a subgroup of G. And that subgroup of G is isomorphic as an abstract group to the semi-direct product, as defined above, just by the map that sends to pair HK to H times K. And this is nothing. This is sort of a nothing statement. Like this is just unpackaging what we did for the dihedral group and like how we got the definition of the semi-direct product in the first place. Like this is sort of just. This statement is basically a tautology once you've digested the definitions. Let me sort of add one. So the remark, I mean, and you usually use this when sort of HK is equal to G. So like in the dihedral group, we use this to write down sort of some type of presentation of the dihedral group as a semi-direct product. And so that's often where this comes up, is you want to present the whole group as a semi-direct product of two subgroups. And sort of in this case, H has to be normal in G. So here I didn't start with the assumption that H was normal in G. I just require that K be in the normalizer. But it's not so hard to check that if you require, if H is a subgroup of G and K is such that HK is a subgroup, and sorry, if H is a subgroup of G, K is a subgroup of the normalizer, and H times K is the whole group, then in fact H is a normal subgroup. So the way I say it sort of has the illusion of sort of. Another comment is sort of, if I stated sort of everything with the assumption that HK is equal to G, like, well, I could always, this group HK lives inside the normalizer of G of H, so I could sort of just also, I could sort of also rephrase this in a slightly different way, where I sort of always take HK to be the whole group G. So there are slightly different ways you can reformulate the same statements that like maybe look on the surface not quite equivalent, but really are equivalent through some simple steps. And probably in the textbook, they don't say exactly what I said here, but they probably say something pretty similar. Okay, good. So this is the recognition principle. So let's do an application. So groups of order PQ, so for P greater than Q prime. So we saw groups of order 15 yesterday. Now let's do groups of order PQ. Well, so suppose G has, so we're just going to classify all of them. So suppose G has order PQ. Well then, and the number of CELOPH P subgroups is equivalent to 1 mod P, and it divides Q. But I mean, like, so that means NP is equal to 1 or P plus 1 or 2P plus 1. But on the other hand, like, Q is smaller than P, so all these numbers except 1 are bigger than Q. So together, we get the NP has to be equal to 1. Okay, so NP is equal to 1. And then, well, let me just say by Cauchy, or by anything, by Cauchy or by the CELOPH theorems, there exists a subgroup. Okay, so let me finish so sub NP is equal to 1, so let H be the normal subgroup of order P. So there's a unique subgroup of order P. There's a unique CELOPH P subgroup. And then by Cauchy, there's just some subgroup, not necessarily normal, of order Q. So there's sort of Z mod QZ. So H is Z mod PZ, and this is K is Z mod QZ. And of course, H intersect K is trivial because, I mean, P and Q are two different primes. So there's sort of an element of order dividing P and order dividing Q is trivial. That's order 1. And so these intersect, but then they have no intersection, but then sort of their product has order, then just the product of the orders, so PQ. So HK is equal to G. Okay, and so the recognition principle says G is isomorphic to, well, H semi-direct K, which is Z mod PZ semi-direct Z mod QZ. So any group of order PQ is a semi-direct product for some, and well, there's some map P. So that means to classify the groups of order PQ, I just need to classify the semi-direct products of Z mod PZ and Z mod QZ and see how many of those are. So phi is a map from Z mod QZ to Z mod PZ cross. Okay, and so I'm not sure if you guys know this result or not, but Z mod PZ cross is always isomorphic to Z mod P minus 1Z. So this is, I will talk, and if you've seen this before, great. If you haven't seen this before, we'll talk about this again when we do field theory. So this has a simple sort of interpretation in terms of field theory. But the point is sort of this automorphism group. So this is equal to automorphisms of the group Z mod PZ. And this is a cyclic group. So the group of automorphisms of Z mod PZ is itself a cyclic group. And so, well, sort of observation 1, if Q does not divide P minus 1, so there is a unique, the only map is trivial. Which implies so G is isomorphic to Z mod PZ just times Z mod QZ. So if you form the semi-direct product with the trivial using the trivial map to the automorphism group, so the only map phi is trivial. If you form the semi-direct product with the trivial automorphism group, with the trivial map to the automorphism group, then you just get the direct product. And then they're like saying you're using the trivial map to twist, but your multiplication by like that is not a twist at all. So you're just getting sort of the direct product. Okay, so good. But it's possible that Q divides P minus 1. So if Q divides P minus 1, then there's a unique sort of cyclic group of order Q. Of order Q in Z mod P minus 1Z. And so let me sort of just, so there are going to be sort of several non-trivial maps. So the non-trivial maps will be, so it'll be Q minus 1 non-trivial phi. So just sort of let me fix any one of them. So I can just fix any one of them. So let me call this phi1, and then sort of pre-compose with multiplication by, I can pre-compose with an automorphism of phi. Or with an automorphism of Z mod QZ. To get more. So any automorphism Z mod QZ that gives me a new map to Z mod P minus 1Z just by precomposition. And so, and then sort of any two non-trivial maps are going to be related by this. So this is maybe just an exercise for you to check. There are probably other, if you can sort of be more concrete than I'm being, but sort of exercise to check this. But you want to check this, plus they all give isomorphic groups. So this is an important point. There can be different maps phi. So phi1 cannot be the same as phi2, but so the semi-direct product with phi1 and the semi-direct product with phi2 are isomorphic. So if we're just classifying groups of order 15 up to isomorph or order PQ up to isomorphism, like we have to sort of check. It's not enough to just sort of say that they're Q-1 non-trivial phi. And so we get Q-1 different semi-direct products because, well, yes, we get sort of different presentations of semi-direct products, but sort of those groups as just groups might be isomorphic. So it's a good exercise to sort of work that out in this case to really see that no matter which choice you make here, you get the same abstract group. And so the conclusion, so if Q doesn't divide P-1, then so Z mod PQZ is the only group of order PQ. And otherwise, there is Z mod PQZ and sort of one non-abelian group of order PQ. So all of these non-trivial phi are going to give the same group up to isomorphism. This is also to isomorphism. But that group and the group these non-trivial phi give will be non-abelian, so it won't be the same as sort of Z mod PQZ. Okay, so yeah, sorry, I've gone a few minutes over again. I apologize. Let me stop there, and I'll stick around if anyone has any questions.